Okay, great. Now I can see. Okay, hello everyone. Thank you very much for being here. My name is Stamatis Tsianikas, and today I will presenting you a joint work that I've done with my group, Nooshin, Yousefi, Jian Xhou, and Professor David Coit. I am a PhD student at the Industrial and Systems Engineering Department at Rutgers, and probably this is going to be my last year. So today I'm going to speak about outage modeling in power planning systems, and we are going to focus in a problem called generation expansion planning in power systems. So first, let me give you an introduction on what this problem is about. So expansion planning problems refer to the monetary and investment and unit investment regarding energy production and storage. And specifically, we studied the case of microgrid. So the problem is, given a microgrid, specific facilities that it is required to serve, specific power plants and storage units, and what is the optimal plan, the optimal policy that we should follow in order to expand the storage capacity on this microgrid. Now, the main problem is that we have stochasticity in almost every element of this kind of problems. We have stochasticity in the generation output of renewables. We have a stochasticity in the load demand, in the climate change. And specifically, the kind of stochasticity that I'm going to talk about today is the frequency and duration of outages. So how do we think about outages, how we can model them optimally in our models, and how the optimization results are affected by the outage modeling that will follow. Now, why is this so important? For the motivation of the problem, we should say that, especially in microgrids that are required to serve facilities like hospitals or other critical facilities, this is a very important aspect because it will affect the reliability of these facilities. The hospital nowadays, they have electronic equipment like blood storage, very life important machinery, etc. So they require uninterrupted service. In most of the current studies to the literature so far, what we've seen in terms of modeling the outages is usually they are modeled by a single statistical distribution, and most of the time this is a Poisson process. In this study, I am going to show you an alternative modeling that we propose, which is basically a superposed Poisson process. I'm going to talk about it in a few. And this is based on the premise that the outages are not coming from a single distribution, but instead they are coming from two different distinct distributions. And let's call them for now regular and severe. As I said, the baseline problem that we're trying to solve is an expansion planning problem. So we want to derive optimal policies for a finite horizon time. It means which storage units should we choose, when should we decide to install them, and how much capacity should we add in our microgrid, in our system. So this is basically a sequential, I would say, investment planning framework for storage. We will attempt to solve this problem using Markov decision processes and reinforcement learning, and I'm going to give you the definition in a few. And finally, the thing that we would like at this point to focus on is the difference between the two outage models, the single Poisson process and the superposed Poisson process. So first of all, let me give you an introduction in MDPs and reinforcement learning in the methodology section. In order to formulate our problem as an MDP, so what is basically an MDP? It's a Markov chain. It's a stochastic process that resembles like a Markov chain, but here we have actions, rewards. So the basic components in an MDP are the agent and the environment. The agent should take actions. The environment, given these actions, should transit the system to a new state and should produce a reward. And now the goal of the agent is to observe these rewards and derive an optimal policy throughout the whole finite horizon. And when I say optimal policy, here we have to take into account delayed rewards, rewards that won't come immediately, but will come in subsequent periods. And why is this important? Because when we decide to invest in a storage unit, in a microgrid, probably the investment cost, the upfront cost that we have to pay is significantly higher than the savings that we'll have. The savings that we'll have correspond to the loss of load cost that we need to reduce, right? But this will come at later periods, so it's important to account for delayed rewards. Now, why is it important, and what was our motivation in order to construct this alternative scheme that I said before, the superposed Poisson process? If we look in table 1, in the KD data provided by the New York State for the company of PAC and Zilog Island, for the years 2012 to 2017. So what we're seeing here is an indicator called KD, Customer Average Duration Interruption Duration Index. This is basically, in simple terms, the average duration of an outage, of an interruption for the whole year, right? If we see the data here, it seems that the data from the years 2013 to 2017, maybe we could say that they're coming from the same distribution. However, the average interruption index for the year 2012 was close to 23 hours, much farther. It was clearly an outlier compared to the other values. So that was our motivation. And this number probably stems from the fact that in year 2012 we had Hurricane Sandy, which affected like 70 million or maybe more population in the whole US. We had outages that lasted a day or even longer, and that's why we are seeing this number over there. And that was our clear motivation on building this alternative scheme. So what is this scheme? First of all, if we consider a single Poisson process, we have a single rate lambda and the number of outages at any time t follow Poisson distribution with a rate lambda t. If we consider this alternative superposed Poisson process scheme, we have two distinct Poisson processes. One with a rate lambda 1 for the regular events, and the other one with rate lambda 2 for the severe outage events. And of course, afterwards, we can define the probability that the outage coming from this superposed Poisson process comes from the regular Poisson process or the severe Poisson process. In our case study, if we check figure 1, we will see how these two alternative schemes change the distribution of the outages. And what we're seeing here is the probability that a specific outage will have a corresponding duration in hours. And as you will see, in figure 1a, most of the outages have a mean around 5, and the variance is equally distributed around 5. However, in the second scheme, because we'll have this in figure 1b, because we have the Poisson process, have outages. Most of the outages are short-lived, we would say, but we have also some outages which could be potentially catastrophic. And this is a very important part in our work. These outages happening around 20 to 25 hours in figure 1b. So the mean duration is the same, but the distribution is not. And our goal is to study how this distribution change will affect the optimization results. Now, for our case study, we studied a microgrid in West Hampton, New York, and we got real data, location-specific data, meteorological and load demand data. We consider microgrid of these facilities that I have in my numerical assumptions: 2 hospitals, 5 schools, 300 residential facilities. The storage options that the planner has is basically 4. We can invest in lithium-ion batteries, lead acid, vanadium redox batteries, and flywheel storage. So we don't have only electrochemical batteries, but we have some other sorts of storage units for options. And the considered stochastic component is the price. So basically, we observe price changes affect the optimization results too. In the results section, what I'm going to show you and what I want to show you is the results of 2 experiments, 2 identical experiments. We ran 2 identical experiments. The only parameter that we changed was the outage model that we used. So I will not give you all the numerical assumptions, detailed numerical assumptions, because again, we are comparing, we try to be fair in our comparison and use only different outage model. So the storage unit prices were declining for both scenarios, and we observed that the optimal policies differ significantly, although all the other parameters remain the same. Just because we changed the way that we perceived outages, and we felt about outages, and we modeled outages, we saw different policies. So let's see the results. In the single Poisson process, first of all, we have 7,000 kilowatt hours total storage capacity after 4 decision periods. So what we see here is the results for both the single and the superposed Poisson process. The blue color corresponds to the single Poisson process. The orange corresponds to the superposed one. So if we see only the blue, we'll see that we have 7,000 kilowatt hours total storage capacity. If we see the orange, we'll see that we have only 4,000 kilowatt hours total storage capacity installed. So this is the first main difference. The second main difference is that the first investment happens one period earlier in the single portion process scenario. So maybe it means that if we think about the single portion process, it's more urgent for us to invest in storage in our microgrid. If we try to interpret these results, we would say that the portion process scenario, the vast majority of outages are short-lived, as we said before. They are not long-lasting, and therefore they could be handled with, first of all, the renewable plants that I may have in my microgrid and a moderate amount of shortage capacity. In the case of the single portion process, though, most of the outages last more than or around 5 hours. So that is the reason I would need more storage capacity in my system. The thing that could worry us is that in the superposed portion process scenario, the optimization results show that we probably do not have a plan how to handle these catastrophic events. And we should specifically...
Try to wrap up, please.
We specifically model and take steps towards addressing these catastrophic events outages. So the focus of this study was to highlight the importance of analytical and proper outage modeling, specifically tailored for microgrid applications. And the open research question is to further study how to deal and handle these catastrophic events. Thank you very much for your attention.
Great. Thank you. Any questions?
So this is Dunbar. Let me first say really nice work in trying to tease out these 100-year catastrophic kind of occurrences separate from a normal windstorm or whatever outage. I would wonder in your formulation of the value of lost load when you have an outage, whether you might also have different value of lost load for a catastrophic event than for a short outage. And let me explain in some ways. At home, if I have an outage for 2 hours, then the food in my refrigerator doesn't spoil. It stays cold enough to be not damaged. So the value to me is different than if I have an outage for a week and I have to throw away a lot of food. Different, that's maybe a minor point compared to what a factory or some other outages might be.
Well, that's a great question. So actually for the value of lost load, we used a study that predicted value of lost loads for the year 2030. And we wanted to use a forecast instead of some real numbers for two reasons. First of all, for the forecast, because we are working in 20 years ahead. So we wanted to use numbers for 20 years ahead. And also because we don't have actually, we haven't properly quantified what is the value of lost load. Now, to answer your question, we use different value of lost loads for different facilities, but this is increasing with the duration outage. But that's a very interesting idea. What we first thought was that maybe value of lost load should be increasing as the years go by. So because there's an electrified future ahead of us, right? We're using equipment more and more in our facilities, even if it's a hospital or if an office or a residential facility. So maybe the value of lost load should be increasing with time, but I think that's a good observation. Maybe we could model the value of lost load to be an increasing function of the outage duration. But again, it would depend on the facility.
Yeah, there has been, this is Frank, there has been some work, mainly coming out of Sandy, to report value of lost load across the duration as well, to try to accommodate the point that Dunbar made. Excellent. So now we're